Hi.
Give me a second.
Do you have a HDMI anywhere? Do you have an adapter? No, you guys have an HDMI adapter?
I have HDMI computer. Is that good?
Okay.
Yeah. Okay. Sorry, I don't use adapter, but yeah, once you plug in, the meeting's already going, like, so you see the plug in, and then I'm assuming you guys don't have a microphone. You can just use this one. Yeah, you can just use this one. You just gotta stand pretty close, though, just for Zoom. Whenever you're ready, we can.
Just.
So when we're doing the slides, I can.
All right.
Here's solutions.
All right, you guys should be ready to go whenever you're ready.
Just to double check, the screen is sharing, right? The screen.
Yeah, the screen sharing over Zoom and everything. You're good to go whenever you're ready.
It should be. I released it like an hour ago. So this slideshow is not what the notebook is.
Okay. Thank you.
Hopefully you have it, hopefully.
Wait, yeah, I just found it.
Okay.
Thank you, thank you. Oh, you don't get it.
Okay, hello everyone. Can Zoom people hear me? Hear my voice? Okay, let's get started. So, welcome to our lab 9, and we will introduce you to CTC laws and also CTC scope decoding, including both beam search and graded search, which you will use in homework 3. So, let's first start with the difference between homework 1P2 and homework 3P2. So the both homework all deal with phoneme recognition, but they are not exactly the same. For homework 1P2, it's more like sequence classification task. So for each input frames, it have one output label. So it's time synchronous outputs. But for homework 3P2, it's very different. It's sequence to sequence task. So that means there's no one-to-one alignment anymore, and that the input sequence can sometimes be so longer than the output sequence. So, but the order can be synchronous. So that causes problems, these two problems. One is the problems of alignment because our input sequence and the target sequence do not have the same length, so we do not know the fixed alignment between them. And also, there's a problem of repetition. That means we have to find a way to deal with the repeated words. And so that's where the CTC jumps in to help the model learn. And in the later of the slides, you'll also know how to use the CTC to go decoding strategy like graded search and beam search to help in the inference part in this task. So let's get into the problem setup. First, in this homework, in the problems of the homework 3, the input and targets are not time aligned. That means the length of the Y, the target sequence, is not the same as the length of X, the input sequence, and they are not proportional either. So you can just refer to this example on the right hand. So this problems is very usually often seen in the task like handwriting recognition and speech recognition, where the timing for each stroke or the timing for each sound is not exact the same. And you can see that you can see that the input sequence, the length is not exact the same as the target sequence that we want to have. So to deal with, but we can see that the order is aligned. That means the sequence go from each stroke or each sound is the same order as you just go through in the target label. So to deal with these problems, you might have some intuition that you can just compress the predict sequence to make it the length matching to the target sequence. But you have to be careful to how to handle the repeating characters in the target sequence. Because if you just compress naively, you can just like merge some repeating part into only one. Then here's an example for your better understanding. So let's say someone just says the zoo words, and we can just transfer this waveform into MFCC features, just like in homework 1P2, and we get the input sequence, x0, x1, blah, blah, blah. Our aim is to transcribe it into the ZOO 3 letters at certain time points. So you can see the problem. The input sequence x0, x1, and so on is not mapping like one-to-one alignment to these 3 ZOO letters at the end. And also, so in this scenario, you might just thinking we can just compress this model's output sequence and to make it the length as the same as the ZOO at the end. But you have to be careful how to handle these two repeating O at the end. You cannot just merge them into only one because it's not what we want. So the key point is that the CTC can help the model learn how to automatically find this alignment between these input sequence and the target sequence. It's a very useful tool, especially in some tasks that the input sequence and the output label have different lengths, and we do not know the fixed alignment. So let's see how does the CTC can handle these problems. So first, let's see the problem of repetition. We can see that when we do the compression, like means to just remove the repeating words in this row sequence. We will see that there are so many row sequence on the right hand side, and all of them can be compressed into the same ZO at the end. But this is not what we want. We want ZOO at end. So how do we handle this repeating O in this scenario? Here's where the break character or blank character comes in. So we just introduce this character, and in this lab, we will use this percent sign to denote this break character. But it can vary, depends on the lectures and the slides. But in our lab, we'll use this percent sign. So you can see after we introduce this break sign between the letters, we can avoid this 2O being merged into 1. And also, we can denote or let the model know like this first 3 Z, continuous Z, can be merged into only 1 Z at the end. So we get this ZOO at the end. We are happy with that. Then after deal with the problem of repetition, let's see how to handle the problem of alignment. You can see that after we introduce the break character, there still be so many alignment between one input sequence to the correct target sequence. And so here's the problems. Which alignment should we take into consider to calculate the loss? So one way is like the Viterbi algorithm is to find the most probable path. So it means like to find the only one path and use that to calculate the loss from there. But it's not the better option. We have the CTC loss. So the CTC loss use the assumption that the sequence have the sequence of the order is the order aligned, and so it can take into consider not just only one best path. It consider all possible valid paths and use that to calculate the expected loss over all possible alignments. So that will be better than the former way. And also for the CTC loss, it have to follow some additional rules. So first one is a monotonicity. That means we only can just move forward in time. We cannot just move backward. And the second is a many-to-one mapping. That means several input sequence can be mapped into only one output label. The third one is the length of the target sequence can be greater or equal to the length of the input sequence. So just to put together with the break character, the order alignment, and these additional rules, that the CTC can find all possible alignments and just assign probability to these alignments. Then we can calculate with this probability to get the differentiable loss. This is the expected loss over all possible alignments. Okay, let's just zoom in and see how it works in detail. So let's get back into this training setup. Our model's output can be like this, the probability of each character at each time step. And our target sequence, just as shown before, is a ZOO letter. We want to transcribe this ZOO letter at certain time step. So you can see our model's output like the probability over all possible character at each time step. But here, to simplify the question of the problems, we only limited to the character that's showing in the target sequence, the ZOO, and also the break notation. in here. This figure will help you better understand the process in detail. So we start with this blank, this empty sequence, and you will see that this is all paths. This is all paths that we can move from the previous symbol to the current symbol. But if you just look closer into it, you will see that some of the paths is not valid. Let's go through together to find which path is valid. So our objective is try to transcribe 0 at the end. So to achieve that, we know that we can, our sequence, our valid path can only start with blank or z, because otherwise we cannot get the z as the first. And our end can only be, sequence can only be end with the second O or with a blank. So in this, given this, we only keep this, the first two as a start of the sequence, and the last two at the end of this sequence. Then let's move on to the next time step. It will be a little bit complex because you can see like some paths just move horizontally, like from blank to blank, and some can move one step down from blank to Z, or just we can skip ahead from blank to blank. But you should be noticed that if we move from blank, just skip from this blank ahead to this blank, it's not valid because we skip this first Z. Because we record that the rules the CTC have been followed, it cannot moving backward. So if we just skip this first Z, we cannot get Z in the later pass. So it's failed, it's not valid. And also, let's just move the similar way, move on. And also we can see if we just skip from this blank to this blank, we skip the first O. And also in the same case, in the similar way, that we cannot get 2O in the later pass, so it's also not valid. Then let's move on. And also here, you see that if we keep this break too long, we cannot get this 0O in time because our aim is to get this O or blank at here, this time step. But if, for example, if we get we keep this as break, and we can first like go to here, the first Z, and then we can skip to this O. But you cannot just skip to this O. Why? Because remember, we have to deal with the repeating words. We have to add this blank into this 2O. So we have to first jump to this blank, and then we get to this O. But this blank is already at the final time step, so we cannot get the 0O in time. So that's also not valid. So here is all the valid possible paths that we can get this 0O. But what we really want to get is to calculate the CTC loss. So to calculate the CTC loss, we need the posterior probabilities, and as shown here is a workflow of your homework 3P1, the CTC part, and just to show you how to implement the CTC step by step. So you first extend the target sequence with blank, as we shown before, to deal with the problems of repetition, and we then to calculate the forward and backward probabilities. Then we use them to calculate the posterior probabilities. Then we plug the posterior probabilities to calculate the CTC loss. Okay, then let's see how it actually works under the hood. To calculate the posterior probability means the probability of all valid paths through a certain point. Let's see, the certain point is at here, the time step 3, and the symbol is O. Then let's first calculate the forward probability. So it's denoted by the alpha t, r, which means the total probability of all possible paths that start from time step 0 and reach to the time step t, which at here is time step 3, and to reach the symbol, which at here is O. So we just calculate like from the left to right to calculate all possible paths to get this O. And you can see that all the red line in the picture shows all the possible transition paths. So we need to calculate, to add up all of these red lines and this possibility that it's also similar to this previous states, which denotes as alpha t minus 1 comma q. It's all the previous states possibility, and we multiply by this yt. This yt SR means the probability of the model to output this symbol O SR at the time step t. Then we get this forward probability. After that, we calculate the backward probabilities. It's very similar as how we calculate the forward probability, but it works in the opposite way. So it's moving from right to left, and it's denoted by beta t comma r. So we start with this at this time step t, time step 3, and symbol O, and we moving from here to this time step t. We sum over all the future states, which denote as beta t plus 1 comma q, that come after this current symbol SR at time step t, and then we multiply by this yt plus 1. This is the probability that the model predicts the next symbol at the next time step. So that it's like we sum over all the future states for the backward probabilities, and for the forward probability, we sum over all the previous states. So at the end, we get this forward and backward probabilities. Then we can calculate the posterior probability. So the posterior probability represents the probability of being in states R at time step t, given input sequence. The R at here is O, and time step t at here is time step 3. And it just consider both forward and backward probability, alpha multiplied beta, and normalize this numerator by this the total probability of all the across all the symbols R prime and across all valid paths, so that after normalization, your value will be between 0 to 1 and sum to 1. So it's the typical probability. Then after we get the posterior probability, we can just plug this into the loss function and multiply by this minus log yt. Then this is the overall loss function that our model wants to minimize during the training. And you can also just consider or just understand this function equation in this way for a better understanding. Then the derivative on the right hand is show you how your loss value just change with respect to your yt. This is your model output at each time step. And this is your model will use during backpropagation to update the gradients. So after we calculate this CTC loss, we can start training. Okay, I'll then pass to Michael to go through the end of it.
Okay, so inferencing is where we have our tests and we're basically predicting our next sequence of having a trained model. So that's the main purpose. And why is that different from our training sequence? Because we don't have a target. So we don't have something that we can predict and test our actual answer from. And we have no sequence of the sequence rules. So we don't have any like duplicate letters where we can cut it out or anything like that. Another thing is, because we don't have a target and we don't have these rules, we can't have a defined output space, like an output length, which means that our decision tree for all of our possible answers is going to be massive. So what are our options? So there's a couple of options. There's greedy search, exhaustive search, and beam search. So greedy search is where we just grab whatever we think the best probable at the moment is. So if I'm currently at the word sequence then the best possible next sequence would be nice, because 0.5 is greater than 0.4 and 0.1. So that's getting the previous or a priori of the highest probability next word. Notice how that the sequence is not the most preferred sequence. The most preferred sequence is dog has. But we're not able to do that because we pick the most greedy solution. And so this representation does not actually show the overall best probability, rather a good probability. So let's show it in a more sequence-to-sequence IDL strategy. So we have our list of probabilities. So we have our ABCD and our time steps, right? And we're decoding our string. So first off, we grab A because A has the highest probability at time 0. And as you can see, 0.391 is greater than 0.14, 0.197, and 271. And then we keep on grabbing the next and the next greatest thing. So it would be B and then A again, and then back to B, which it's a good probability, but it's not the most representative of the actual sequence that we're going to estimate. So now there's another side to this, which is exhaustively testing every single possible case. Obviously, this would find you the highest probability sequence, but unfortunately, our computational time would be so massive that it's not worth it in the very end. So the last thing and the middle ground to this is beam search. So this is where we grab the top K best candidates, which would be our beam size, and we compare our top K candidates, and we maintain our top K candidates. So how we get our top K candidates is we get what we got. So the star, so for example, we could get the dog, and we multiply it, we have that as 0.4, and then we multiply it by our next running sample, and we compare that to the next competing candidate, which would be the nice, which would be 0.5, and we compare it to its candidates, which would be woman, house, and guy. So, and also in this example, the beam size is 2, and let's continue on with inferencing of sequence to sequence in the terms of IDL. So I have our list of letters here, and our sequence length is going to be 4, and our beam width is going to be 3. So our beam width going to be 3 are going to be our top K candidates are going to be 3. And because our top K candidates are going to be 3, we're only going to be mainly comparing and contrasting 3 different options. So we start off, we can see that we have dash A, B, and C, and we'll just calculate our score from time step equals 0. So we have 0.14, 0.391, 0.197, and 0.271. We just grab the top 3 best candidates, which would be A, B, C. And obviously, that's our beam width. So our beam width would be the top K candidates, and now we can continue on with the next time step. The next time step would be all the possible combinations of A, B, and C because they are our current beam width. So it would be A dash, B dash, C dash, and it would be AA, and since AA has a repetition, it would be A solely, AB, AC, BA, BB, and so on and so forth until the end of our sequence of possibilities. So the scores would be calculated based off of our time step 1 multiplied by our a priori time step, which would be 0.391 times, for the first example, A dash would be 0.391 times 0.275, because the first path is A, and then our dash is the second option. So we multiply our current score by the next time step. So what we do is we do that for every single possible combination, and then we get our new beam with out of that. So when it comes to the sequences, A dash maintains a high probability, AB maintains a high probability, and AC maintains a high probability. So now we maintain those as our current sequence, and we ignore all the other possible sequences. So for example, B dash doesn't exist because it's not the highest probable, nor does C dash work. The only ones that work for us now are A dash, AB, and AC because we have held them as our highest competing candidates. So now what we do is we grab these 3 candidates and we find all of the possible probabilities between them, and then we compute the next sequence. So this would be ABA, which would be maintaining whatever AB is, multiplying it by the next B candidate, which would be 0.10 times 0.26. So that's AB right here, our old score, times our current B. Then it's also AB, which is going to be AB times AB, or B, sorry. And then we have a little bit of a tie, but we still have ABA and ACA because AB and AB are overlapping. So you would have to sum those two up. Let's continue. So now we have ABA, ACA, and AB, and we have our next time sequence, and we grab the top of those. So obviously we're having much more overlap. You have AB overlapping with AB, ABA overlapping with ABA a lot, and ACA overlapping with ACA. So it also simplifies our lives, but it makes it harder at the same time because we're going to have to sum across all of the possible options. And then this is a much more big interpretation of what Beam Search is doing. So we're just grabbing the top K candidates of each step, so A, B, C, and then we maintain that as our A priority, and we go to the next sequence and see what the best output is. And so it's A dash, A, B, A, C, and then we maintain that to see which of the bests are from that sequence, and it's A, B, ABA, AB, and ACA. And then we do that so on and so forth until we get our best candidate from holding those beams. So here's another example, another representation with a different set of probabilities and different solution set. So we have our SOS, which is like the start of our sequence, and then we have our dash AB, which is our highest probability, and we continue that time step, so on and so forth, until at time step equals 3, we have AB, A, AB, and BAB. So here's a little bit of a code implementation that we can go over, but it's not going to be useful for this lab. So I just have it here, and that is it. So let's go over the notebook now. So I believe this is a notebook. Nope, one sec. This one. Okay, so the notebook. So we're just going to be implementing from. It's going to be image to sequence recognition. So we're going to have somebody written out sequence on an image and converting it to text generation. And it's time for you guys to do up to checkpoint 1, which would be to the start of Beam Search. And we will go over the answers in a short bit. So we'll probably give you guys 10 minutes, hopefully, to get here. Okay. So let's go over the first checkpoint. So I'm gonna do it on my actual copy. Here. Okay, so we want to get the most probable class at each step, and since we're given a log probabilities, we probably want to get the argmax of them, the largest value of them. So what we're gonna do is we're gonna get the it's a torch function, argmax of, and it's log underscore probs, comma, and then our dimension is going to be 1 because that is where our probabilities are. It's for our batch, I'm believing. And so now let's continue to the next checkpoint. So for sequence, so when we're specifying a specific sequence, what we're going to be doing is we're going to get our indices and we're just going to do it batch-wise. So it auto-completes, but yeah, you're doing it across this batch. As shown right here, it's throughout our batch for our indices, and so we just get per batch. Now for our sequence, to stop it from consecutive, we have to do torch.unique consecutive, which is such an interesting function that no one knows about. And then the last thing, which is removing blank tokens and converting it to a list. So that's going to be our s.item. And then for s in sequence, if s.item is not equal to self.blank. Okay, and that should be all for our greedy decoder, and now we'll give you time to go over our beam decoder. Probably come back in 5 minutes. Okay, so now we'll go over Beam decoder. So it's specifically stated to use CUDA CTC decoder for Beam search. And then this is alongside using dot contiguous. So, and also changing the input shapes. And the CUDA CTC decoder states a certain input shape parameter that they want. So we could easily go over what that says. And then the command page, it says, where is it? Branch, frame, and num tokens. So we have to flip the frame in the batch because of how our data is ordered. So wrong notebook. And then so what we do is we do self.decoder, and then and then we have, oops, and then we have our log underscore probs dot transpose. So we're transposing it here because we have to for the decoder to work. And we make this contiguous for our inputs. And then we also do lengths dot two, and then we change this to an int 32 because it's easier to compute alongside, I believe we have to. I did not spell lengths correctly. And then we make this contiguous. Now for the decoded batch, we just grab the best sequence. So we grab the very x0 of the tokens. And then for x in decoded. So that's it, I believe. Yeah. So now we'll be doing the training pipeline. So that's the next thing. We'll probably give you like 5 minutes to do that. Okay. Okay, let's go over the training sequence now. So we have our input lengths. So that's going to be a fixed size of inputs. It says right here, fixed size of inputs for a CTC. So we're going to have to do something like torch.full, which makes it so it's all fixed sizes. So we get our batch size. One sec. I'm struggling. Wait, up. Underscore size, gamma. Okay, and then we have our log underscore prob size exactly the same. And then the curve. And then we have our calculated CTC loss. So this is just our self-dot criterion that we have initialized above. I believe it's here, CTC loss. And then it's just the log probs, the targets, the input lengths, and the target lengths. So this is what you call in the function. You could look it up if you need to, but just take my word. And then now checkpoint 9, which we'll go over as well. Checkpoint 9 has the decoded. One sec. So we're basically just going to call the decoder on this. So self dot decoder. And then we're going to call our log probs. And then as well as our input lengths. So you should be able to run your whole sequence off after this, and hopefully it works. Hopefully there's no errors. As well as there is a checkpoint 10 down here that you should do afterwards. So, okay. So the last 5 minutes, we'll probably go over the last checkpoint, and that's it. Okay, let's go over the last checkpoint. The last checkpoint is, let's see. Let me also go down here. I believe it's checkpoint. So for this checkpoint, we're just going to be doing basically what we did in the training sequence, where we do torch.full. Has it written there. So we have our log probs this dot size. So this is for our predictions, I believe. Yeah, it's our inferencing. So this is where Beam the coder and Greedy the coder are going to work. And so we have our torch.full of our, like we only want one sequence as an output. And so, and we're getting our log probabilities of that. And then what we're gonna be doing is we're gonna be getting the decoder that we've trained. And then we're just gonna use our log probs and our input length to get whatever value we have next. If I can spell trainer right. Trainer, there, okay. And that should be it for this lab. So I hope you guys enjoyed it as much as I did.